Hello. In this video, we are going to derive an expression for the reversible adiabatic expansion of an ideal gas. First, we recall that du, where u is the internal energy, is equal to C sub v, the heat capacity at constant volume, times dt. This is simply a rearrangement of the definition of the heat capacity at constant volume, which is the change in the internal energy per unit temperature. Next, we recall the first law of thermodynamics. du is equal to dw plus dq, where w is the work and q is the heat flow. In the case of an adiabatic compression or expansion, this dq term is identically equal to 0. So therefore, in this case, du is equal to dw. So here is where we've applied the fact that our expansion is adiabatic. In the first two lines, I have expressions for du. If I set these equal to each other, I get that Cv dt is equal to dw in our adiabatic case. We realize that if the only work that is being done is work of expansion, then dw is equal to minus p dv, where p is the pressure and dv is the change in the volume. In lines 3 and 4, we have expressions for dw, which we now set equal to each other, which gives us that Cv dt is equal to minus p dv. Now we make the assumption that our gas is an ideal gas, for which we can apply the ideal gas law, PV equals nRT, which we will do a minor rearrangement on to solve for the pressure P. We have that the pressure is equal to nRT divided by V. And as our motivation is, we have an expression here for the pressure, and we're going to substitute this expression, nRT over V, for P in the fifth line. Thus we have Cv times dt equals minus nRT dV over V. In our next step, we're simply going to take this expression and divide each side by the temperature T. We get, therefore, Cv dt over T is equal to minus nR dV over V. In our next step, we are going to want to integrate each side. On the left-hand side, we have Cv times the integral of dt over t between t1 and t2. We consider the 1 to be the initial circumstance and 2 to be the final. So that on the right-hand side, we have minus nr, and now the integral goes from v1 to v2, where v1 is the initial volume and v2 is the final volume of dv over v. Now we apply the fundamental theory of integral calculus to get that the left-hand side is Cv times the log of t between the limits of t1 and t2 minus nr times the natural log of v between the limits of v1 and v2. In the next step, we're going to make use of the properties of logarithms, that the logarithm of b minus the logarithm of a is equal to the logarithm of b divided by a. This gives on the left-hand side Cv times the natural log of t2 divided by t1 is equal to minus nr times the natural log of v2 over v1. In the next step, we're going to use the fact that minus the log of b over a is equal to plus the log of a over b. The fact that by flipping the sign here, we flip the fraction inside the logarithm. As a result, the left-hand side stays the same as it was before, but now the right-hand side is, there's no minus sign, so we have nr natural log, and the fraction is now v1 divided by v2. In our next step, we're going to make a relatively simple algebraic manipulation in that we're going to divide each side by n times r. Now the left-hand side becomes CV divided by nr times the natural log of T2 over T1 is equal to the natural log of V1 over V2. Now we're going to simply assign this coefficient CV over nr to a new symbol, just the letter C. We remind ourselves of our substitution that we're letting C equals CV divided by nr. So this gives us now that C times the natural log of T2 divided by T1 is equal to the natural log of V1 divided by V2. And now we're going to make a use of another property of logarithms, that if I have a coefficient in front of the log, I can bring the coefficient as an exponent. So we use this property that a constant times the log of x is equal to the log of x to the c power. So that gives us the natural log of T2 divided by T1 to the c power is equal to the natural log of V1 divided by V2. And we're going to use yet one more property of the logarithm, that if I take e to the natural log of x is simply equal to x. So this is the property that we use, e to the natural log of x is equal to x. So that gives us on each side that now we have T2 divided by T1 to the c power, no log, is equal to V1 divided by V2 with no log. We are careful to apply a property of exponents, that if I have an expression inside the parentheses raised to the c power, that the exponent applies to both the numerator and the denominator. So that gives me on the left-hand side T2 to the c power divided by T1 to the c power, which is equal to the right-hand side, which is V1 divided by V2. We have one last step, which is to cross-multiply to get our final expression. So this gives us that V2 times T2 to the c power is equal to V1 times T1 to the c power. And we have our result. I thank you very much for your attention. Have a good one.